let me mention, this is, I think you'll agree, this is very, very beautiful, the action for a particle and its coupling to the electromagnetic field. I just want to show you quickly what the action is for electromagnetism itself. Okay, so electromagnetism, the action for Maxwell. So this is the following. I claim we should integrate over space-time. It's a four-dimensional integral. And then, well, what can I write in the action for Maxwell? I want it to be Lorentz invariant. I want to depend on F. What can I do? F squared. There's nothing you can do, right? So then I claim that you could put any constant here. The right constant is this one, to agree with Maxwell. And then actually we want to know how it couples to currents, electromagnetic currents. We need to put those in too. We already did that, because if you think about it, the current carried by a particle is just q times its velocity. That's the natural current, right? So basically you need a delta function on the world line, but essentially the current carried by a particle is the only thing it can be is q times u mu, right? So that is the term, and in the four-dimensional picture we write it this way: j mu a mu. Okay, so the claim is that if I vary this guy, I'm going to get Maxwell's equations. Let's just check that as Maxwell. So delta S is integral. Now, when I vary this guy, F squared, so I get a factor of 2, minus 1 over 2 mu naught F, I'll write it this way. F upstairs, I'll vary the downstairs guy. And then I vary with respect to A, but I leave the current alone. It doesn't depend on A. The current is assumed to be just fixed, independent of A. So this is J mu delta A mu. In fact, I'm going to write it this way with the J upstairs and the delta A mu downstairs. What is delta F mu nu? Well, F mu nu is d mu a nu minus d nu a mu. So it's just d mu nu delta a nu minus d nu delta a mu. Okay? So what I do, as usual with actions, I integrate by parts. If you're in so I'll just integrate by parts here. I get a minus sign, so I get yes, in fact you notice, obviously this is antisymmetric under mu and nu, right? So these two terms will be identical because they're both contracted with the F. So I could just cancel one of them and remove the factor of 2. So there's only one term now. Makes life easier. Now I integrate by parts, and I get plus 1 over mu naught d mu F mu nu delta A nu. And then over here I have J. I'll relabel the mu index nu delta A nu. And so I have d mu F mu nu is minus, this is supposed to be 0, this equals 0 for all delta A nu, and so this gives me d mu F mu nu is minus mu naught J nu. Okay, so that shows that the obvious action is the action for Maxwell. Now maybe at the end of the course, if we have time, we will see that, remember I introduced this T mu nu last time, the energy momentum in the electromagnetic field. We'll see that when we do gravity, we can actually derive that formula in one line, one or two lines from the action. Everything comes from the action. We'll get T mu nu, the energy momentum tensor from S. Maxwell. Good, so now we're going to get on to noether. She is an absolutely remarkable person in history who defied all odds and did something which Einstein and Hilbert and all the leading mathematicians and physicists of her time could not do. So she was, first of all, denied. It's an amazing story. So she was a Jew in Germany, and she was not allowed to take an undergraduate degree because she was a woman, and so they said, okay, you can audit the classes. And so she sat in on the classes in math, and then finally they agreed to let her take the exam, even though she wasn't really registered as a student, and she did much better than anyone else. And so finally they agreed to give her a degree. I think she was the first woman ever to get a degree in maths from that university. And then the struggle continued throughout her career. And then Hilbert and Weil and others realized she's a clever person, and they invited her to come to their seminars. She was allowed to teach in her university, but without pay. So she never was paid as a professor, and she never held a title in the university in Germany. And she went to the seminar with Einstein and Hilbert, and they were I mean, conceptually, relativity and GR is very, very difficult. They were struggling with this, and she saw right through it all, and as I say, understood what is energy in special relativity, what is energy in general relativity, that's even harder, which Einstein and Hilbert were completely confused about. And she wrote two amazing papers in 1917. And then she left physics. She said physics is too trivial. And she founded the field of modern algebra in mathematics. And she's very, so if you ask a mathematician who is Emmy Noether, they say, wow, Emmy Noether is amazing, you know. But you say, what about Noether's theorem? They go, ah, it's a triviality. Okay. But Noether's theorem became the foundation for 20th century physics. It's all about symmetry. I mean, anytime you hear the word symmetry in this institute, you have to realize the importance of symmetry goes back to Noether. She realized symmetry is the key. And then the whole of 20th century physics really became a search for symmetry. And those symmetries control the laws of physics. That goes back to her. But she was completely unacknowledged for at least half a century. She never won a prize for anything, as far as I know. And then, unfortunately, she died when she was quite young. She came to the US, and she was to escape Nazi Germany, and died a couple of years later because she got cancer and had the wrong medical treatment. And so a very tragic story. So that's why we have Emmy Noether Fellows and all of that at Perimeter. It's a big emphasis. We need to highlight such amazing people. Okay, so Noether theorem. So as you will see, it's a very clever idea, but rather simple to state, very deep to think through. So the statement is the following. It's all about actions. So it only applies if you can formulate your theory using an action. And what the theorem says is that for every continuous symmetry of an action, there is a corresponding conserved quantity. So that's a very profound statement. And so let's talk about a continuous symmetry. What is a continuous symmetry? A continuous symmetry is some transformation which leaves the action unchanged. And we're normally going to only require that it leaves the action unchanged up to surface terms. Okay, generally we're going to not worry about surface terms. You should, in principle, worry about them. But when you vary an action, the variations in between the two endpoints can be arbitrary. And so the equations of motion do not depend on the endpoints at all. So a continuous transformation is defined by its infinitesimal version Okay, so if I do a continuous transformation like a rotation, I can always imagine doing a very small rotation. And that's very convenient for many purposes, and in particular it's sufficient for noether's theorem. All you need is the small transformation, arbitrarily small transformation. So imagine I have some dynamical variables. These are my dynamical variables. And t is some time. Okay, it won't be the usual Lorentz time. For this action, the t would be the lambda. It's some parameter on which the dynamical variables depend. So this is whatever the right time is. And the transformation is a change from these ones to some other dynamical variables, which are defined to be qa plus epsilon. This is a small parameter. Times xa of q and t. Sorry, this is q and q dot and t. Okay, so the idea is I'm going to take some trajectory of the system, and I'm going to change it to another trajectory, which is equal to the old one plus some small change, and I'm going to allow this small change to depend on the coordinate and the velocity and the time. So this x quantity doesn't have to be small, but there's an overall parameter which is small. So some small change to the trajectory depending on all the properties of the trajectory. So we call this a symmetry of the action Oops. Oh, I wrote on the wrong one. Sorry, I'll leave it there and write on this one. So we call this a symmetry of the action if for constant epsilon, the action of q prime, q dot prime, and t is equal to the action of q, q dot, and t up to surface terms. Okay, so somebody gives you an action, you change q to q prime, you express q prime in terms of q this way, you calculate away, they give you the xa as well, and when you calculate away, if you can show that your new action equals the old action plus surface terms, then that xa, that particular xa they gave you, is a symmetry of the action. And this is only supposed to be true to order epsilon, just to first order in epsilon. So Noether's proof so the clever part of it, you see, you define the symmetry for epsilon being a parameter which is a constant, doesn't depend on t. But Noether realized that you can always regard this change as an actual variation of the action. Why not? Variation of the action says you replace q with q prime, which is q plus delta q. And this could be arbitrary. Okay, so Noether said, consider making epsilon a function of time. An arbitrary function of time. Okay, then this formula, let's call it 1, then the variation 1 is a perfectly allowable variation and hence we must have delta S equals 0 up to surface terms using the classical equations of motion.
What do you mean by surface terms?
Just the kind of things we did here. We always integrate by parts with actions, right? So when you have an action, you have something like x dot squared minus v of x dt. If you want to vary this and get Newton's equations, you write the variation, I'll put a half there, integral dt, x dot delta x dot minus v prime of x delta x. Now I integrate by parts, right? So this is equal to a surface term, x dot delta x, minus integral dt. And now I've integrated by parts, so I get, so plus, let's put a minus here, x double dot delta x minus v prime of x delta x. Right, so that's the surface term. Okay, and then I say this must be 0 for all delta x. This implies this this implies that x double dot plus v prime of x equals 0. So when we're deriving equations of motion, we can generally forget about surface terms. If you want to be a little bit more careful, what you say is when I define my variation, I should insist that the variation vanishes on the boundaries. All right, so I consider trajectories x of t with the initial and final points fixed, and then I insist that when I vary the path, I don't vary the initial and final values of x. Right, so then this would be saying delta x equals 0 at the endpoints. Okay, and in that case, the surface term will be 0. But Noether's theorem is a local statement. It's not going to depend on the endpoints. And so essentially, you won't have to worry about the endpoints. It's only when you do try to be more careful you have to worry about the surface terms. Okay, so that's a variation. So I'm going to plug this into my action. I'm going to imagine epsilon as a function of t. So I'm going to get an answer, right, for the action. So now you just think, what could I possibly get for an answer, given that this was a symmetry of the action? What is the only possible answer I could get? The answer must be in the following form: integral dt epsilon dot times some function of q dot and t. This is perfectly fine. So the only things I get, I'm only interested in things to first order in epsilon. What could I possibly get to first order in epsilon? Well, I could get this, because if epsilon were a constant, this term would vanish. So that's consistent with this being a symmetry of the action. Right? So that's fine. And the slightly more subtle one is I could get this too. I could get that, because that's a surface term, right? And so if epsilon is a constant, that is a surface term, okay? And so that's not going to contribute to any, that's not going to, if epsilon is a constant, that variation is not going to contribute to the equations of motion. Okay, so this is all you could get, basically. So that's our argument. It's the only possibilities for what you could get if you allow epsilon to be a function of t, and if you assume the action had a symmetry. So the epsilon here is a function of t. Now, it follows from this that this is equal to integral dt, just integrating by parts. This is epsilon d by dt of k minus j, right? Just integrated the first term by parts, plus surface terms. Okay, but then, because this is a perfectly allowable variation, it must be that when I use the equations of motion, this vanishes, right, for arbitrary epsilon of t. So this will be equal 0 by equations of motion for all epsilon of t. Because for any epsilon of t, that's an allowed variation. The variation of the action should vanish up to surface terms, and so this must be 0. But of course, if that's true, then this quantity must be 0. So it follows that d by dt of k minus j equals 0 by the equations of motion. And that's my conserved quantity. K minus J is the conserved quantity. All right, so it's a very nice prescription. I come up with some symmetry, the x's. I vary my action. I work out the coefficient of epsilon dot, work out the coefficient of epsilon. It has to be a derivative. Go through this machinery, and I will come up with a conserved quantity. So, kind of surprisingly, this is not very well explained in textbooks, in my view. Steven Weinberg's textbook on quantum field theory is one of the most thorough, incredibly comprehensive book on quantum field theory, and I invite you to look at his derivation of Noether's theorem. It's very far from optimal. Tony Z also has a whole chapter on it, also, I think, very suboptimal. But so not often presented very nicely. So let's do classical mechanics, just to see how this works. Okay, so non-relativistic mechanics. We're going to take the action to be the integral dt of the Lagrangian. And the Lagrangian is a function of q, q dot, and t. Right, so that's the starting point of the Lagrangian formalism in classical mechanics. And what I'm supposed to do is vary this. And of course, as you know, delta S equals 0 implies the Lagrange equations of motion, that dl dqa is equal to d by dt. This is for all delta q, d by dt dl dq dot a. Okay, so those are the Lagrangian equations of motion. I assume you've all done this in classical mechanics. Okay, so let's do Noether. So Noether says delta q a equals epsilon a. I don't really want to do that, do I? Noether. Let's first of all do translations. So what's a translation? A translation is just a shift in the coordinates. All right, so if translations, if these coordinates were, let's say, x, y, and z, then the Noether transformation would be just a shift in the coordinates. And so this would be a small constant vector in any direction. Okay, that would be a translation. But Noether is going to make this a function of time. That's the clever trick. So it follows that the variation of the velocity is the time derivative. So now let's calculate the variation of the action. Obviously, what I do, I'm varying q, so I take the partial derivative of the Lagrangian with respect to q times the variation of q, which is the epsilon. And then I do the same with the velocity, partial derivative with respect to the velocity times the variation of the velocity, which is this guy. And what must be true is that this must be 0 up to surface terms. okay, for all epsilon of t. This must be 0 by the equations of motion for all epsilon a of t. Now, so if L is translation invariant, okay, if L is if the Lagrangian is translation invariant, then we have that dL dqa equals 0. So for constant epsilon, the variation of the Lagrangian is just proportional to dL dq, and this must be 0. So that term should be 0 if the Lagrangian is translation invariant. And so now I will require this to be 0 for all epsilon a being a function of t. So I just integrate by parts, and then it follows that d by dt dL dq a dot equals 0. And what is this? This is nothing but momentum conservation. Okay, why? Because this is the definition of the momentum in classical mechanics. You take the Lagrangian, and the derivative with respect to the velocity is defined to be the momentum. So the argument shows that the reason momentum is conserved is because the Lagrangian was translation invariant. Okay, so none of this would be particularly new. It gets more interesting when we go to other symmetries, and in particular energy. I mean, you can see from the Lagrangian equation of motion that if dL dq is 0, then d by dt of dL dq dot is 0. So this would not surprise anyone. Momentum is conserved if the Lagrangian doesn't depend explicitly on the coordinates. More interesting is time translation. So if the Lagrangian is invariant under time translations, we must have that there's no explicit dependence of the action on time. And now let's go through the argument again. Delta S is equal to integral dL dq. Oh, sorry, I should say what a time translation is. So time translation on the coordinates means that qa of t goes to qa of t plus epsilon. That's what a time translation is. So I take my trajectory, and I just shift the time. So that, of course, is equal to qa of t plus epsilon times qa dot of t. So this is my, what I called x. X for a time translation, the quantity x is just the velocity. And likewise, qa dot of t will go over to qa dot plus epsilon qa double dot of t. That's what a constant time translation will do. Change your velocities by an amount proportional to acceleration. Now let's do Noether's calculation. dL dqa epsilon qa dot. See what I'm doing here? Calculating the variation of the action. It's the variation of the Lagrangian times the variation of q. This is delta q. right? So dl dq delta q. But the Lagrangian also depends on dl dq dot. And this will give us epsilon qa dot dot. Okay, so this is the variation of the velocity, is epsilon qa dot. Sorry, the variation of q dotted. Right, so in general, if epsilon is a function of t, I've got to take the dot of the whole thing. So that's the variation of the action where epsilon is a function of t. Now I'm going to integrate by parts, as usual. So this is going to give me integral epsilon, then dl dq a qa dot minus d by dt dl dqa dot times qa dot. So integrate by parts. And ignore surface terms, as usual. This must be 0 for all epsilon. So the claim is yes. So this kind of looks like this is true. So it must be that this actually must be d by dt of something. Okay, by Noether's argument. When I did this variation, if it was a symmetry, I have to be able to write it as epsilon times d by dt of something. Now this is not obviously d by dt of anything, right? I'm not allowed to use equations of motion at this point. This is not obviously d by dt of anything. But you know from Noether's argument, it must actually be d by dt of something. So what could it be? Well, obviously to get the first term, this looks like dl dt, right? dl dq, dq dt. So let's just try this, d by dt of L minus, and what does this look like? Well, it involves dl dq dot and q dot. Okay, so maybe it's that. Well, let's try. That's basically all it could be. So let's try. What is this equal to? Well, dl dt, L does not depend explicitly on time, right? So L only depends on q and q dot. So this is dl dq times qa dot plus dl dqa dot times qa double dot. Right? That's the first term. And the second term would be, you see, I get the qa double dot from here, so I get minus dl dqa dot, qa double dot, and bingo, this cancels. Right? And now I've got to differentiate this guy, so I get minus minus d by dt of dl dqa dot times qa dot. And what do you know? That's exactly what we had. Okay, so Noether was correct. It is d by dt of something. And the thing it is d by dt of is this. And so now we've proven that since this equals 0 by the equation of motion for all epsilon of t, we've proven that d by dt of this equals 0 by the equation of motion. And what is this? This is a well-known quantity. What is this in Lagrangian mechanics? The Lagrangian minus, so basically this is L minus P Q A dot. Alternatively, you could, or it's equal to minus P Q dot minus L. What's that? Hamiltonian. Okay, and it's well known the Hamiltonian is conserved if the Lagrangian has no explicit time dependence. So it's just saying that the noether quantity you obtain in this machinery is exactly the energy, or the Hamiltonian, in classical mechanics, right? So this is just showing that Noether's procedure reproduces everything known from classical mechanics. Now, of course, it gets much more interesting in relativity because the actions are more involved. Yeah?
Did we just guess that that was... How would you... You had that.
Yes.
How do you just...
Yes, you've got this awful expression. Well, Noether tells you it must be d by dt of something.
So why did you just guess that it was that?
Oh, because I looked at this and I said L is a function of Q and Q dot. Right? How could I possibly reproduce this expression? Well, one way I could do it is just d by dt of that. This would certainly give me dl dq, right, times q dot. And then, of course, I get dl dq dot of q double dot. So I can see I can get this term from d by dt of something. This term I can get from d by dt of this times that. There's an ugly extra term in both cases, and they cancel. Okay? But Noether's argument tells you they have to cancel, or there has to be a way of doing it. Okay? So it's really very, very clever. So I hope you can see why she thought it was a triviality, and also why everyone else was amazed. Of course, this is just the beginning of her first paper. What she does is generalize this in much, much more interesting situations. And people are actually still writing research papers exploring Noether's second paper. Okay, so now let's do it for relativity. You see, so the point is the following. Noether suddenly tells you why there's a conserved quantity. All I have to do is look for a symmetry, which is continuous, like a shift in time, a shift in space, and I'm guaranteed there's a corresponding symmetry. So now I know why there's a momentum, why there's an energy, why there's an angular momentum. It's just because my action is invariant under the corresponding symmetry. So relativity, this gets a lot more interesting, because let's start from this action. Okay, this you're just taking on faith, this minus m naught c. You'll see why we choose it minus m naught c shortly. obviously I'm going to get the momentum out as the coefficient of the variation. But so far this is just a choice I've made to define the constant. So in fact, what I'm going to do is choose c equals 1 now. Okay, so I don't have to keep track of c. Just to simplify the algebra, you can always put it back in. But let's choose c equals 1. We're in units where the speed of light is 1. And let me furthermore, see, I've got this lambda parameter in there. Let me now do the following. Let me choose, so I have some world line, ct and x. You see, the time is, because the world line is time-like, there's a one-to-one correspondence between time, actual time, t, and lambda. Right? So every point on the world line has a unique value of the time t. So one convenient choice for lambda for a time-like trajectory is lambda equals t. Why not? Let's just use the real time as the parameter along the curve. So now things simplify. This becomes minus m naught integral. So lambda equals t square root. And then we have, so here we'll have dt dt, which is 1. So I just have a 1 minus x dot squared. Okay, where x dot equals dx dt. And I've chosen units where the speed of light is 1. So in this particular coordinate system, that's the action for a relativistic particle. Now it looks like classical mechanics, but a little bit more complicated because the Lagrangian is not quadratic in the velocity. It's more involves the square root. So the momentum p, and so we already derived this from translations. The momentum was defined to be the coefficient of the quantity which multiplies the epsilon, right, for a translation, should be d by dt of the momentum. And so the momentum is dl dx dot. So this is equal to plus m naught. So when I take this is my Lagrangian, dl dx dot gives me minus x dot over the square root. I get a factor of a half from the square root, but a factor of 2 because this is x dot squared. And so this gives me plus m naught x dot over root 1 minus x dot squared. So this is nothing but gamma m naught v, where v x dot is v. Okay, so we started from the action. We defined the momentum to be the quantity you get when you vary the action by space translation, and that's what it is. The energy, E, by the same argument, the energy is precisely this quantity, or actually with the minus sign. So the energy is dl dx dot x dot minus L. And so this is equal to, this is m naught x dot squared over square root 1 minus x dot squared, just using this line. And then minus L is minus, it's now plus m naught times the square root. And you see I can combine the two terms just by multiplying through by root 1 minus x dot squared. So I get m naught x m naught times x dot squared plus 1 minus x dot squared over square root 1 minus x dot squared. And so that's equal to m naught over root 1 minus x dot squared. So that's equal to gamma m naught. So the momentum is gamma m naught v, and the energy is just gamma m naught. Of course, when I do that, E is approximately, for small velocities, will be m naught plus 1/2 m naught x dot squared. Just as before. So it includes the rest mass energy and the kinetic energy. But in relativity, we have higher powers of the velocity. Okay, so we see that this noether procedure. Let me just plug. We see that the noether procedure tells us exactly what the energy is, and what the momentum is. Can you see how I put the C's back in? I know energy is units of kinetic energy, half mv squared. There must be a c squared there, just by dimensions, okay? So the noether procedure tells you exactly what these quantities are. In other words, it tells you to take seriously the leading term here, the mc squared. That really came out as the energy. Okay, now, of course, the importance of this, why is energy important anyway? Well, energy is important because in a coupled system, if I couple my particle to fields and other particles, the only thing I know is that the total energy is constant. Right? Energy is exchanged between the different components. So the energy of the particle shouldn't be conserved. But what I know is the total energy. The total energy arises by varying the total action in Noether's way. And each subsystem contributes an energy in exactly this way. So I know when I couple my particle to an electromagnetic field, then the energy of the particle, this would be energy of the particle, right? This would be momentum of the particle, are given by these. And of course, there's some energy in the field as well. And then what Noether's theorem guarantees is the energy in the total is constant. Okay? But that energy in the total includes the rest mass energy of the particle. So this is really the correct derivation of E equals mc squared. It comes from Noether's theorem and the action. Okay, are there any questions? Of course, when we write down E equals mc squared, this is what we think of as m. This is the m. It's the effective mass of the particle. Yes?
When we were talking about the action for Maxwell's equations, we wrote F mu nu.
Yes.
But why couldn't we write something like F mu nu, A mu, A nu?
Oh, in the action? Right, so this was the action for Maxwell. So you're right. What would be wrong? as far as Lorentz invariance goes, this would be fine. Okay, it's Lorentz invariant. Yes, what?
Sure.
Yeah, so that's 0. That's 0. Yes, it's probably 0 in multiple ways, actually, because it's also... I mean, even if I had another B mu there, I think it would still be problematic, because it only involves one derivative. So, for example, it won't be time reversal invariant. In order to write an action which is time reversal invariant, you need 2 derivatives. So this would only have 1. I don't know. But certainly the A mu NU doesn't work. So yeah, I encourage you to try anything else you like. Of course, you could write, what you could do is write this squared. That would be fine. That's a good action for Maxwell. There's nothing wrong with that. In the end, this is exactly what people do when they do effective field theories. They consider all the objects you have and just write down anything you like in the action. Okay? A lot of assumptions go in, one of which is that the action should be a polynomial in the fields. Why? Because that's simple. There's no profound... I mean, the relativistic action is not polynomial in the velocities. I mean, the square root is not a finite polynomial of the velocity. But typically people assume this. Then you say, okay, imagine... So basically you're saying, imagine I could Taylor expand my action in the fields around 0. What am I allowed? Well, I could have this term, and I could have this term, and I could have all the other terms. And then the argument is the following, that if this term has dimensions, right? So we already saw that f goes like 1 over length squared. So this is 1 over length to the 4th. So you can already see that the action for this term would be dimensionless. That's nice. The action has to be dimensionless. But if I write this term down, this goes like 1 over length to the 8th. So what I need to do is introduce a length here to the 4th, some fundamental length. And then the argument is, because this has dimensions of length to the 8th, length to minus 8. So now the action will be dimensionless again. But I've introduced some fundamental length. Now the argument is that if I am doing physics on long wavelengths, like the ones in this room, or the ones we're interested in, the size of the field of this L will be much larger than that L. So provided this L naught is really small, I'll actually never see this term. Okay, and that's the rough idea of effective field theory. You do a Taylor expansion, introduce dimensionful coefficients, which you guess involve length scales much smaller than your experiment, okay, the ones that you probe. And then if that is the case, you can neglect such terms, okay, except when you go to very small scales. So you will see the literature is full of arguments like this about you take the standard model of particle physics and you add extra terms and you put in dimensional coefficients. And then sometimes you even use these terms to do calculations and you try to fit the coefficients to real data. Okay, that's a perfectly legitimate procedure. But it does introduce new parameters. And it does rely on this idea that the Lagrangian should just be a polynomial in the fields. Yeah.
You mentioned time reversal invariant.
Yes.
What conservation law comes out of that?
Good question. So remember, Noether's theorem only applies to continuous symmetries. Continuous. Time reversal is whoop. I can't do a small time reversal. We did small symmetry operations to get Noether's conservation law. Time reversal, it's all or nothing. I just reverse the time. So there's no conservation law for a discrete symmetry. Parity is another one. If I just invert all my coordinates, spatial coordinates, that's some kind of symmetry, but it's not continuous. There's no small version of it, so there's no conservation law. So, yeah, let me just pose a question. Think of a conserved quantity. I mean, what's a conserved quantity that is not energy, momentum, angular momentum? Is there anything else you know of that's conserved? Charge, electric charge. Why is electric charge conserved? What's the symmetry that corresponds to electric charge conservation? So I've already kind of mentioned that it's something to do with gauge symmetry. Okay, but I'll just state this, okay, that charge conservation symmetry is a result of the fact, charge conservation is a result of the fact that when you do quantum mechanics, you're free to rotate the wave function by any phase, constant phase. That's a continuous symmetry. Okay, I can just take my wave function of everything, rotate it by a phase. And then the probability is the same because the phase doesn't come into psi squared. That symmetry is has the consequence of electric charge conservation. That should blow your mind. Good. It's really a quantum symmetry, but it does also relate to gauge symmetry. Yes?
I don't even know if this is like a question, but if you rotate something physically a little bit,
Yeah.
you can see that happening, but I thought you couldn't see the overall phase change.
Okay, good. Good. Yes. So if somebody took let me think of the way of saying it. You see, Noether's statement is very precise. It's saying that if the action is unchanged when I do this rotation, so you must rotate everything, including you, okay? If there's reason to believe that the laws of physics would be exactly the same if I rotate everything, then you'll get a conserved quantity. So if you're looking at a system, you can see it rotate. That necessarily it means something's changed physically. So, yeah. So maybe, just think of it in a simpler way. When I write down, if I've got some particles interacting by some force, we would write down, mx double dot equals this force. So let's, for example, for gravity, we'd write g, m1 would be, g x1 minus x. So we write down some formula like this, roughly speaking. There must be an m here. This looks a sensible law. Why? Because if I rotated my coordinates, nothing changes. I rotate the x, I rotate the x1, I rotate the x. I should have summed over the other particles. Right, all the other particles are influencing particle number 1. But if I rotate everything together, the equation is the same. Okay, if the force involved some other term, like some vector, some special vector, you'd say, well, this is a very strange law because it's saying that somehow in the universe there's a special vector which enters my laws and makes them not the same if I rotate everything. So then there wouldn't be any symmetry. I mean, for example, if in the universe there was a gigantic magnetic field traveling across space, then the laws of physics would not be rotational invariant, and there would be no conservation of angular momentum. So it's only because the interactions between particles do not single out any place in space, any direction in space, that you have a symmetry. So you say, when I want to describe motion, you see, this is the paradox. To describe the evolution of the world, we need coordinates. We don't know how to describe the motion evolution of the world without coordinates. We've got to use some coordinates. Okay, but there are aspects of those coordinates which are redundant. We know that. I mean, when I choose that as my coordinates, they're nowhere fundamental. You know, x, y, and z. That's not fundamental. It's just a convenience. But it's a convenience which has some redundancy, because I could pick any other system, and I really am describing the same physical system, so it shouldn't make any difference. So it's the fact that we introduce this redundancy that leads to the conservation laws. So, yeah, and energy is the consequence of the fact that the universe doesn't change from today to tomorrow very much. Okay? And so there's no reason when I describe some experiment, I shouldn't have to mention the time since the Big Bang. Right? When I throw this in the air. You really shouldn't care about how long it's been since the Big Bang. So there's some special time should not enter. And that means there's a redundancy in the choice of time. And that means there's an energy which is conserved. Yep.
So if you had a conformal field theory, is there a conserved charge for like the special conformal transformations?
Yes. Yes. Let me think about that. So, in general, so people often do conformal field theory without any time. They do Euclidean conformal field theory, right? And then all directions are the same. And then noethers, you have to slightly change your interpretation of noether because no coordinate is any different than any other. So that's one thing to say. But yes, the point is when people do conformal field theory, so I've told you this already, there are 15 parameters in the conformal group in 4 dimensions, right? There are the 10 Poincare generators, then there's scale symmetry, which makes 11, and there are 4 others, which are called the special conformal generators. Every one of those corresponds to a conserved quantity. All 15 of them give a conserved quantity. But you have to be a little bit careful with some of them. You see, for example, I told you the Poincare group has 10 parameters. Right, so where are the 10 conserved quantities? Well, the answer is that, let's see, 4 translations. So that would give you, so let's do Poincare. It's a little bit easier. We have 10 generators. We have the lambdas. We have the translations. Okay, so 6 and 4. These correspond to boosts, which there are 3, and rotations. There are 3, and these correspond to translations in space and time. Okay, so that's Poincare symmetry. So this one will give us the energy. This one gives us the momentum. These 3 give us the angular momentum. So we've used up those 4 and these 3, but what about these? Are there conserved quantities corresponding to the boosts? Okay. And actually they are, but the reason you have to be careful is these boosts inevitably involve time. Okay, so it's a symmetry which involves time. The XA, these generators I mentioned, actually involve time. And so when you do a boost, the quantity you infer to be conserved is time dependent. Okay, so you say d by dt of something which involves t is a constant. Okay, so it's just a little bit more subtle. With these ones, the quantities you write down do not involve time explicitly. But the conservation laws for boosts do involve time explicitly, and likewise for the special conformal generators, they do involve time explicitly. So they may not be so useful, in a situation with space and time. But in the Euclidean theory, they're definitely very useful. So in 4D, this is the special conformal group. I'll actually define it later in the course. In 4D, it has 15 generators. In 3D, I don't remember how many generators. Anyone remember? I don't remember. But the interesting thing is that in 2D, how many generators does it have? Special conformal group. You know? Turns out it has infinite. It has infinite generators. The reason for this, I mentioned the connection with complex analysis. So you know the fact that in complex analysis you can say Z prime is any function of Z, where Z is x plus iy, and this function is arbitrary. So that's essentially the reason why in 2 dimensions the conformal group, special conformal group, is infinite dimensional. The consequence of that is you have infinitely many conservation laws, which is very helpful. When you're trying to solve a theory, it's very, very helpful. So 2-dimensional conformal field theories are particularly simple because you have infinitely many conservation laws. Any other questions? In fact, you know, the amazing thing is that in 4D, the standard model of particle physics is almost exactly special conformal invariant. There are very few terms which break this symmetry. Okay, one of them is the Planck mass. It's a mass, so it introduces a scale. Can you name another one? There are 2 more in the standard model. 2 more scales which break conformal symmetry. So there's the Planck mass. There's another one. Another 2.
Higgs mass?
Higgs mass is 1. So that Planck mass is 10 to the 18 GeV. The Higgs mass is 126 GeV, right? And there's one more. There's one more scale in standard physics. It's basically the mass of the proton. It's the QCD scale, which breaks conformal symmetry. And that one's actually much more interesting because it arises due to quantum effects. But there are only those 3 numbers in the standard model that break scale symmetry. Otherwise, everything else is scale-free. Maxwell's theory is scale-free. Dirac's theory of the electron is scale-free, apart from the electron mass, which comes from the Higgs. So physics is almost completely scale-free. And yeah, it's very fascinating. So many people believe that at a fundamental level, physics should be exactly scale-free. Okay? And then the scale emerges, the scale dependence somehow emerges. There's lots of work on that idea. Any other questions? Yes?
Is there a reason to believe that physics should fundamentally be scale-free other than this?
Yes. The reason is physics should not be about units. Kilograms, meters, seconds, amperes, coulombs, joules, blah, 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 right? That can't possibly have anything to do with the reality. The reality should be just about information, pure numbers, and then there's no scale. So you could say that I was lucky enough to know John Wheeler, who invented the term black holes and wormholes and many other sort of famous words. Amazing, amazing person. He was the supervisor of Richard Feynman, of course. And so John Wheeler coined the term it from bit. It from bit. Okay, so what is bit? Bit is a bit of information, like in a computer, a 0 or 1 is a bit. And it is a real thing. So John Wheeler said, you know, what are real things? They're just information. So he always said he believes in it from bit. Okay, then more recently people start talking about it from qubit, but they're just really copying Wheeler. And one of the funniest seminars I ever went to, I went to Moscow. There was a big physics conference, and Wheeler was invited to give a plenary talk. And he stood up and he showed one slide. And the slide was a picture of household objects. Okay, there was a key and a lock and a pail for water and various other things. Okay, and his whole talk was that it from bit. And all these very tough Russian physicists were looking at him, scratching their head, thinking, has he completely lost his mind? But then the irony was, you see, he was always like that. So he would always talk in ways that people thought are really strange. But then his ideas, 20 or 30 years later, would always be at the center of attention. Okay. He was just way ahead of his time, always. So people thought he was a complete joker, but now the joke's on them, because everybody's chasing it from qubit and all this. It's just the same philosophy. In fact, if you look in Misner, Thorne, and Wheeler, the book, the very big book on gravitation in the library, it's a big, thick volume. It's a very famous textbook on general relativity. There's a whole chapter there on logic and pre-logic and all this kind of stuff. So, yeah, so many people believe that units should not be important in physics. I think it's very appealing, and I think there's lots of evidence that's true. Okay, so in particular in cosmology, which is my field of interest, if you look at the universe, it's the simplest thing we know. The structure of the universe on large scale is simpler than the structure of an atom. It's just a fact. You need 3 parameters for the hydrogen atom. You need 2 for the universe. Okay? You look at the shape of the fluctuations in the universe. They are scale-free. It's a very good approximation. There's no scale. All scales are equal. So the universe just telling us, you stupid idiots, there's no scale. Okay? It's telling us directly. Just like the universe is telling us Planck was right, quantum mechanics is correct. You know, the Planck spectrum, when you measure the microwave background, you get the most perfect black-body spectrum. So the universe just tells us all these things. It usually takes us a while to figure it out. But right now, the universe is absolutely telling us there is no scale in physics. So I think we're just not smart enough to figure out how to write a theory down that describes that. But we're trying. Any other questions? Yes?
I might be missing something, but going back to the term that we wrote down that described the coupling of a free particle to an electromagnetic field, it doesn't appear to be engaged here. Do you have anything to say about that?
Say that again?
It doesn't appear to be gauge invariant.
Yeah, great question. Very good question. This doesn't look like it's gauge invariant, because A changes under gauge. But actually it is, okay? Because if A mu goes to A mu plus D mu F, this is now the change in the action is D mu F, which is d by dx mu, right? And so this is df d lambda. And so then that's a surface term. So yeah, it is gauge invariant. It is and it isn't. Okay, because it's a surface term. So now surface terms, let me see. Yes, so you have to be a little bit careful about it. That's the main thing. So the variation of the action will depend only on the gauge transformation at the endpoints. Okay. Now, if I define this integral around a closed loop, I will get 0. because there's no endpoints for the integral. And likewise, if I fix the endpoints and, yeah, let me think. What am I trying to say? So the statement is that integral a mu dx mu around a closed loop is absolutely gauge invariant, right? But the action change only depends on the endpoints. And so you can see there might be some subtleties in various situations. And the most famous one is the Aharonov-Bohm, where what you do is you have a particle going here and a particle going there. So this is particle 1 and particle 2. And they both move. There's a magnetic flux here, but no field strength. So locally, everywhere in space, you only have the vector potential, and it's pure gauge, meaning the F mu nu is 0. So locally, the A mu is the derivative of something. So naively, you may say there's no physical effect at all. But actually there is, because the integral along here is not the same as the integral along there. The difference between them is this closed integral, and it turns out that the magnetic flux through the middle actually matters. Okay, so there's some subtleties, and it's good to be aware of that. But it's almost gauge invariant. Okay.
Does that change the trajectory of the particles? Or
No.
What does it do?
No, nothing. It changes the phase of the wave function. Okay. So the particle going below, so in fact this phase turns out precisely the phase 1 is equal to psi 1, the wave function going this way equals the wave function going that way times this phase, integral a dot dx. And then there's an h bar, there's a q, and this is exactly the Aharonov-Bohm phase. So this comes exactly out of this term in the action. And of course we have integral of a around a closed loop, integral a dot dx equals integral b dot ds, because b is curl a. So by Stokes' theorem, the flux through the middle is exactly this term. Okay? So this was the amazing thing Aharonov and Bohm realized, is that two particles which separate and come back together, and neither of them experience any electric or magnetic field. Nevertheless, you can detect how much magnetic field was in between them by comparing their quantum mechanical phases. And even that is included in the action. It comes from just this term. Yeah?
If all it changes is the phase, how do we observe the exact
Interference.
Oh, okay.
So basically you send a beam on one side, you send two beams and recombine them,
Just the fact that they
and you crank up the magnetic flux in the middle, turn it up, turn it down, and you will see that the number of particles you receive at the other end changes because the interference is either constructive or destructive. So it's really observable. But it's a non-local effect, you see. So it's an example of a quantum effect which is completely non-local. You can't say it happened here because of something there. No, it happened because of some global property. Quantum mechanics is inherently much more non-local than classical. Okay, I think I better quit before I collapse. So see you next Tuesday, I believe. All right. Hope you enjoy your quantum courses.